Have you understood the demonstration? Is it okay? I'm not absolutely satisfied. There is some non-optimal steps, but principally it is right. It's correct. So this is the our standard Poisson structure, but expressed in terms of L tilde. Okay, it's the sum of standard linear and constant Poisson structure, and this is what we call the lambda structure. So the structure with some parameter. We know that this Poisson structure it is just the standard Poisson structure in terms of L. So we know how its center is organized. So it is generated by such as spectral functions on a parameter L. And that's why we can express it in terms of such an operator. The only thing which is not satisfied for me, that this is not L, it is L tilde. There is some trick to proceed to the good coordinate. So I prefer here to be L. So we know that these functions. So if you remember the lemma, it says the following: that the center of this generic bracket produces involutive family for both brackets. Just a moment. So we need the following thing, that trace of L plus Z C K so it has an expansion trace L K plus Z it is the sum of E J K I from 0 to Z power I. Okay. Yep. So then we say that JKI commute with respect to both brackets, and it means that commute with respect to the linear bracket. But for doing so, we have to realize that this is the so I have to consider L Z C. This we denote by L tilde, and L tilde is equal tilde 2 minus z p c2. So let me go differently. So we have the Poisson bracket L z, which is the standard 1 plus z 0, which is p L2 plus z p C2. We need to describe the center of this bracket, of the generic bracket. And to do this, I introduce L tilde, which is L plus C, and I show that L tilde maybe minus C. L tilde is just L, which is P L2, and L is equal to L tilde plus ZC, and that's why we can write here P L tilde 2 plus yes, that should work, that P C2. This means the following, that to describe the center of this algebra, we have with this bracket Z. We need just to consider the center of this algebra in terms of L. So the center of Z bracket in terms of L tilde is just the center of in terms of L. Okay, so and what is the center? It is given by the trace of L star plus K. So this is just a calculation. This is just a calculation. So if there are some I should think about it. So the statement is correct, and I'd like to give another demonstration of the statement, but it should work from this lemma too. So I need the following statement, that that trace of L Z C K trace of L
well, plus or minus, it doesn't matter.
Yes, that's true. That's true. So I will demonstrate that this is 0, and it will mean that all the coefficients of this series are else 0. So first of all, do you remember that L of Z with L of U is equal to P z minus u L of z plus L of z this was the Poisson bracket in the Gaudin model. This is the Gaudin model with 1 point. Okay? But we discussed the Gaudin model with n points. This is its generalization to the one point. And if we write it like this, it is just L of C. I'm sorry. It will be better. So it is equal just so this constant doesn't interact with other terms, so it's just the same thing, and it means that it has the same expression. And I would like to write here it is equal to P z minus u L 1 of z plus C C1 plus L of u plus 1 of C. So I'd like to add this this component. So to argue this equality, I have to demonstrate that P C1 plus C2 is equal 0. Okay, and this is right because of the following consideration: minus C1 plus C2 P. So what is it? We can I will write it as follows: C1 plus C2 P, because P is involution C2P. And then to expand this, so if you conjugate an element by P on both sides, it changes the component. So it will be C2 plus C1 P minus C1 plus C2P. And it is obviously 0. Okay? So, and it means that so we now denote this function as L of z plus C, and we have demonstrated that L of z by L of u is P P over z minus u L1 of z plus L2 of u. And as we know, this matrix form of the Poisson bracket means that all the coefficients commute. So this follows. Okay, I'm sure that the argument from the Bihamiltonian structure are also efficient in this consideration, but I will think and explain you later. Now we pass to the home tasks. Do you remember? They were a statement about Stachel systems. Please, who want? Please take this part of.
You mean HR commute?
Yeah.
First, let's do it for two-dimensional.
Please start for stating the problem.
The problem is we have capital lower.
Zero. Mm-hmm.
In which x and y are canon equal.
Yep.
So first solve it for two dimension. I use some signal to make it more lazy. I write as H1 and R1. It means okay. I use such notation. I think there's some better method, but I just do the partial derivative. So first, both to this, and it's by the Leibniz rule. First, all this term related with this, so we could write as we put all partial h on the left hand side. And or r on the right hand side. First one, and second one would be much easier because they are not derivatives with x1, so this would be just to rewrite it in a good way, I use some simplified signal signs, and so let's call this one kx. And you see now it is a linear function. We could write it as
Mm-hmm. Mm-hmm.
And we just use to solve this equation by what's that guy's
Kramer.
name? Yes.
Kramer
Yes.
rule.
So we call the depth of this thing is b. And so the solution should be
Mm-hmm. Mm-hmm.
And we could do the same thing for y. You see nothing changed, just substitute x to y.
Mm-hmm.
And I write the result. And then if you hope to calculate you see it is just this 2 guy
Mm-hmm.
minus this 2 guy, so it's
Mm-hmm. Mm-hmm. Yes, yes. Have you coped with the general case?
Yes, you could do the same, but I think we could just observe to get the result of the form.
Uh-huh.
That I think it should be correct. We write as the equation. If you do the derivative, it would be minus I write this thing directly. It would be minus in which Sij should be or J X Y. Compare with this thing.
Mm-hmm.
It's a general case.
Okay. S. S. What
think J is this metric.
Uh-huh.
This metric.
Uh-huh.
I think
And delta is just the derivative?
yes.
Uh-huh.
Like this.
Uh-huh.
I think it looks correct, I guess.
Yes, that's okay.
And say the same thing by Gaudin. What was that again? Anyway, it should be like so we introduce it should be I k and
Uh-huh. Mm-hmm. Okay, yeah.
Just to generalize it, I think the same method works.
Okay. UIK, what is it? Uh-huh. Okay. Yes, I agree. Yeah.
So that's it.
Mm-hmm.
We have the conclusion.
Yes, I understand. Yeah, very good. The next problem was about the Gaudin model. So the question was to understand better the roles of different coefficients in the generating series of Hamiltonians. So I have a little bit different demonstration, but principally the same. So the only thing to use is that the rows of the rows of these metrics commute between themselves. The elements from different rows commute between themselves. Okay, and it is sufficiently strong statement which allows to calculate the commutators. But you have done the same thing principally. So now, as we discussed before, the SF2 matrix, Lux matrix for the Gaudin system is a matrix like this. And the characteristic polynomial is lambda square minus a square of z minus b square b of z c of z, and this is the following the sum of H0 So the question was to choose between the coefficients. So we know that the coefficients of this expression commute within themselves, but so the question was to understand what is the rank of the Poisson bivector and how many Casimir functions should exist in this case, and to express the Casimir functions and non-trivial Hamiltonians in terms of the coefficients of this characteristic polynomial. Do you understood what is the structure?
I'm not sure. Well, yeah, we could just calculate the trace IO squared.
Of A?
IO squared.
Uh-huh. So the statement that the algebra generated by E2 and HE1 is an involutive family, is an involutive subalgebra in SL2 and so, but to understand the integrability, we need to find the Casimir functions in a good number and to find the non-trivial Hamiltonians. So do you have an answer?
I have some guess, I think.
What think other participants of our discussion? Have you understood the problem?
Understand, but not understand the solution.
And the problem?
Not really, I think.
Okay. So you see, we will have an examination quite soon. So if you don't understand the problem, it's better to consult your colleagues. Would you say what ideas?
First, if you well, just consider this guy. Just consider this.
Uh-huh. Okay.
And what is this guy? This guy is, in fact, if you calculate this, it's just yes.
Mm-hmm.
My guess is to calculate this guy.
I think it is double or.
I did.
Okay. Mm-hmm. Yes.
And we have did it once in the course, but you want me to do it again to calculate this?
It's expansion on that, or what?
I mean, in our case,
Mm-hmm. Yes, but what to do? What?
calculate direct.
What do you mean?
I mean,
Expansion.
yes, maybe.
I don't remember. Please write it. Okay.
Just, in fact, we need just to note it.
Yep. Yes. Yes.
So we expand it, and we could be right to 2 sigma independently. So that's why we could get the form looks like this.
Yes.
So, but I think
Do you know what's the residue of the function at the pole? Residue.
that's,
Residue.
I mean, Cauchy is
Do you know?
complex analysis.
Yes. Would you like to apply it here? Because these coefficients are the residues, of course. So these coefficients are clear to calculate, isn't it?
I think it is just 2 times. I think it just that's 1 or 2.
Well, so HI2 is simple to calculate. It's the coefficients at the pole of the second order. What we have to take in this product to get the pole of the second order. No. HI2 is just a trace of phi I square without summation. Without. Because in your product,
Yes.
to get the second order pole, you have to take the same residues here to multiply and to take the trace. And to get HI1, it's a little bit tricky, but it is also simple if you remember what's the residue of a function.
If we get rid of all this term, what we left are actually, I think,
Maybe
sorry.
that. Uh-huh. Yes, yes, I agree. Yeah, maybe twice.
Yes, yes.
Mhm. Okay. What do you think about them?
So, you mean which one is Casimir function?
Yeah.
I think the second one. I mean the second order one. And this one.
Me too, but why?
Well, it was the way you asked last time. Last time you. I think from our this polynomial it should be.
Do you remember the Poisson bracket? How it is organized?
Check.
Without Poisson bracket, it's difficult to find Casimir functions. You don't remember
What remember?
the Poisson bracket? The Casimir function, we can understand that something is Casimir by using the Poisson bracket. What is the Poisson bracket here?
You mean commute with?
We had everything, yes. Casimir function commute with everything with respect to the Poisson bracket. But it depends on the Poisson bracket. If you choose another Poisson bracket, you will find another center of the Poisson algebra. So to answer the question, we need to remind the Poisson bracket of the model.
You mean this?
Yeah. Yes, that's right, but it is difficult to extract the knowledge about Casimir function from this form. So it's better to remind the initial definition of the Poisson bracket. In terms of the matrix entries of phi. Do you remember the form of phi? Okay, it was the general form for the GLN. For GLN. For SLN, it was a little bit specialized. So phi I is HI, EI, FI minus HI. These entries are just generators of the eth copy of SL2. Understand? But now return to H to HI2, which is just the trace of phi I square. And what will be your right answer?
You mean to check?
Yes. Uh-huh.
You mean to check which one? Or it is, we know it is.
Maybe you know this.
I mean, it is for SL.
Yes, for SL.
It is
Yeah.
Casimir.
Yes. It's a Casimir function in the corresponding copy of SL2. So you see, in this expression, then you just expand the characteristic polynomial. The highest coefficients are just the Casimir function in the corresponding copy. But these functions are how to say, they depend on different copies. So you see, this is an expression of this type. Okay, let us calculate the number of Casimir functions. Are there? Is it sufficient, or what is the dimension of our phase space? No.
Phase space.
Yes, phase space. Yes. How many variables we have at the beginning? You have n sites, so you have particles, and over each particle you have SL2. So we have 3n variables.
You mean count all the 5?
All variables which are in the definition of our system. So at each pole you have 3 variables. You have 3n variables at all. And you have n Casimir functions. So the dimension is 2n. So in fact there is another gauge symmetry of the model. It is the common conjugation of the slux operator, which is not dynamic, which is not interesting. So that's why we have in fact 2n minus 2, which is the dimension of the genuine integrable system. And that's why, you remember, we have zi, not zi, but yi, zeros of C of z, wi values. So as C of z is has n minus 1 zeros. Do you understand why? If not, I will explain with pleasure. So C of z is the sum of f z minus z e, product of z minus z e, C0 product from 1 to n, from j from 1 to n minus 1, z minus yj. So it's of degree minus 1. When we express it in such a way, it has some polynomial of degree n minus 1. So it has n minus 1 zeros. And these are the good variables on this symplectic space. But initially we had 3 n-dimensional space. It is not. It couldn't be symplectic in general. Okay, thank you very much. So now it's better understood. Okay, let us think a little bit about Bihamiltonian formalism. About the Bihamiltonian formalism. And the first problem will be to work a little bit with the Schouten condition. So let's remember that P1 and P0 are compatible Poisson bivectors if this Gaudin bracket is 0, so I express this condition as some differential equation. So it is the sum of pi 1 is d pi dk dxs, and then I take the symmetrization okay, P2 and plus the same thing is P1 gk dxs, and here also we have a symmetrization. Cyclic, not symmetrization, cyclic permutation. Cyclic permutations. Let us discuss this operation. So the Gaudin bracket on vector fields is just the commutator of vector fields x, y are vector fields. Do you remember what is the commutator of vector fields? A vector field on manifold is such an expression and the commutator is a vector field with such a coordinates xi so it's the same thing as to consider the Lie derivative of the vector field y with respect to the vector field x minus the inverse operation. So the Lie derivative is the procedure when you just differentiate the coefficients, okay, along the vector field. Yes, of course. But now we are interested in expanding this operation to polyvector fields, in particular to bivector fields, which are our Poisson bivector. So Pij d over dxi d over dxj. So we will consider this object as the wedge product of two vector fields. And first of all, I will define x, y z x z y plus x y z. So you see, here is the commutator of vector fields, but now we get an operation which commutate a bivector with a vector field. So the first problem is to understand that the extension of this operation to bivector field says the following, that this condition zero condition is equivalent to one condition. Let's try to do it. And let us start. We start with the situation with one bivector field. One bivector. So with the situation that P1 is equal to pi 0. This is just PL2. This is PC2 or something, for some coefficient. So I demonstrated that they're compatible, but it is very good to demonstrate it just directly considering this Schouten bracket between two brackets. Very good exercise. So the next problem will be the problem we are discussing now. So to compare Schouten condition, this one, condition and this Schouten bracket. This one. So this is just this Schouten bracket of two bivectors. And another question will be to find a quadratic Poisson bracket compatible with the linear Poisson bracket of the open Tode chain. Open Tode chain. Are the formulation clear? Is it clear? Okay. If it is clear, I'd like to return to the argument shift method. All was okay, but I need to explain it more clearly just for me. So we consider it L of Z, which is L, which is the same L Gaussian generating function, plus Z multiplied by an auxiliary constant matrix. And I started to study such a characteristic polynomial. So my statement was that all the coefficients of this characteristic polynomial commute between themselves with respect to the standard Gaussian Poisson bracket. So this is the argument shift method, which means that I shift my matrix by an auxiliary matrix C, and I consider all the coefficients of this expansion in traces of invariant functions. So I would like to demonstrate this applying the lemma about Bihamiltonian structure. So if we have the pencil of Poisson of compatible Poisson structures and the central element with respect to the generic one, just expanding this central element, we get a huge involtive family, and this is the particular case. So to do this, yes, I denote this by L tilde just by some simplification, and then I calculate the following thing, that L tilde Poisson bracket with L tilde is just L with L, so it is P L2, but I'd like to write it as L tilde 2 minus Z P C2. So I know that traces of LK are central, but I'd like to write it as trace of L tilde minus ZC K. So I know that this function is central with respect to this bracket. And by the lemma, it means that all the coefficients of this function with respect to Z commute with respect to both Poisson bracket. By the lemma, we get that, for example, trace L tilde K, which is the zeroth coefficient in this expansion on Z, are commute Poisson commute with respect to both to all brackets. I think I need all coefficients. The sum of I from 0 to K, I Ki, Poisson commute. No, there is some additional argument I should verify. That firstly, by the way, just the traces of powers of L tilde Poisson commute with respect to all bracket and with respect to the standard Poisson bracket, standard quadratic Poisson bracket. No, I should work better on the subject. Okay, you have the home task. Are there appeared some question about the formulation? If not, we stop for today. Good continuation. See you next week.